All right, let's dive right in. Today, we're tackling a really classic physics problem. It's one of those puzzles that looks pretty simple at first blush, but it's hiding a much deeper lesson about the fundamental laws of motion. We're going to break it down piece by piece.
So where does this challenge come from? Well, it's from this legendary book, i.e. Irodov's Problems in General Physics. For anyone who's studied physics or engineering, you know this book. It's basically a rite of passage, famous for problems that are super tough, but also really elegant. They really make you think.
And here it is, problem 1.182. Let's just soak in the setup for a second. We've got a cart, it's being pulled by a constant force F. But here's the catch. There's a hole in the bottom, and sand is leaking out at a steady rate. We'll call that rate mu. Our job, figure out the cart's acceleration and its velocity at any given time t, knowing it started from a dead stop.
Now, your first gut instinct, and hey, it's a totally logical one, is probably to say, okay, the mass is changing, so I'll just figure out the formula for mass at time t, and then I'll plug that into F equals ma. Seems like the quickest way to the answer, right? Well, that's the trap. That simple approach actually misses a huge piece of the physics puzzle here.
So if the simple F equals ma is a dead end, how do we actually solve this? Well, we have to dig a little deeper and use a more fundamental, more powerful version of Newton's second law. And that means we need to start talking about momentum.
What you're looking at here is the whole story. That F equals ma on the left, that's the one we all learn in high school. But it's really just a special case. It only works when an object's mass stays the same. The equation on the right, though, force equals the rate of change of momentum, that's the real deal. It works for any system, including our leaky sand cart.
And just as a quick refresher, what is momentum? You can think of it as an object's quantity of motion. You know, its oomph. You just calculate it by multiplying its mass times its velocity. It's why a big, slow-moving truck can have just as much momentum as a tiny, fast-moving baseball.
Okay, so here's the absolute key. When we look at the rate of change of momentum, which is dmv over dt, we have to use the product rule from calculus. That means we get two parts. One part is m times a, which looks familiar, but we also get a second part that has to do with the changing mass. This is exactly why this simple F equals ma is wrong for our problem. It's literally missing half of the equation.
So, thankfully we don't have to derive this from scratch every time. Physicists have already worked it all out for us. It gives us a specific tool for exactly this kind of situation. It's called the variable mass equation, but a lot of people know it as the rocket equation. Why? Because it's the exact same principle that explains how a rocket pushes itself forward by shooting fuel out the back.
And look at this. Right here in the source text, Irodov gives us the master key. It's equation 1.3j. This is the formula that correctly handles any system where the mass is changing. So let's take a closer look at what's going on inside this thing.
Here it is, written out nice and clean. Now, don't get intimidated by the letters, we can break it down. That mdv over dt on the left side is just mass times acceleration. Easy enough. On the right, you've got F, which is the external force, plus this new character, u dm dt. That's the part we really need to understand.
So let's go piece by piece. The term on the left, m dv dt, that's our old friend mass times acceleration, or ma. The F is just the net external force. In our problem, that's the constant force pulling the cart. But that last term, u times dm dt, that's the new player. This is what we call the thrust term, and it accounts for the momentum of all that sand that's leaving the cart.
The thrust term is everything, and the most important, most subtle, and trickiest part of this term is that little letter u. Now listen closely. This is not just any velocity. It is the velocity of the escaping sand relative to the cart. You have to imagine you're sitting on the cart. What speed do you measure for the sand as it falls out horizontally? Getting u right is the secret to the entire problem.
Okay, that's enough theory. We have our master equation. Now it's time to roll up our sleeves and actually use it. Let's walk through a step-by-step guide to solve this thing once and for all.
Here's our game plan. 5 simple steps. First, we'll write down a formula for the cart's mass at any time. Second, we'll figure out that super important relative velocity, u. Third, we'll plug it all into our big equation. Fourth, solve for acceleration. And finally, we'll integrate that to get the velocity. Nice and logical.
All right, let's do it. Step 1 is pretty straightforward. The mass at any time t is just the starting mass m0 minus how fast it's leaking, mu, times the time t. But step 2, this is the light bulb moment. The problem says the sand spills through a hole. It just drops straight down. It's not being thrown backward or forward. So from the perspective of the cart, its horizontal velocity is 0. That means our critical variable, u, is 0. And if U is 0, guess what happens to the entire thrust term? Poof, it vanishes. It's gone. Our big, complicated variable mass equation suddenly becomes this. We're left with the changing mass times acceleration equals the force F. Now, wait a second. That looks a whole lot like F equals ma, right? The difference is we got here the correct way by considering momentum first and proving that the thrust term was 0.
Now, with just a little bit of algebra, we just divide both sides by the mass, we get our final answer for the acceleration. It's the force, F, divided by the mass at that exact moment. Now check this out. As time goes on, that bottom number, the denominator, gets smaller and smaller. That means the acceleration is not constant. It actually gets bigger and bigger as the cart gets lighter.
And for our very last step to get from acceleration to velocity, we have to integrate that acceleration function over time. When you do that, it involves a natural logarithm, and this right here is the final expression for the velocity of the cart at any moment t.
So, we solved it. We got the answer. But just getting the right formula isn't the real prize. Let's take a step back and think about the crucial physics lesson that was hiding inside this clever little puzzle.
Here are the 4 big takeaways. First, whenever you see a problem where the mass is changing, your brain should immediately scream, momentum. Use F equals dmv dt. Second, remember that this leads you to the variable mass or rocket equation with that all-important thrust term. Third, solving these problems always comes down to correctly identifying u, the relative velocity. And finally, the really cool part, you can have an object that's speeding up faster and faster, even with a constant force pulling on it, just because it's getting lighter.
And I'll leave you with a final question to chew on. What if we flipped the problem on its head? Instead of sand leaking out, what if sand was being dumped in from a stationary hopper hanging over the track? The cart is moving, but the sand being added is initially still. What would the relative velocity u be in that case? Would the thrust term still be 0? I'll give you a hint. It's the very next problem in the Irodov book, and now you have the tools to figure it out. Thanks for working through this with me.